Mike Godson from Clark College's Automotive Department will share his perspective on the direction of the automotive industry in his presentation, Driving the Future Automobiles in the 21st Century. Traditionally, the Vice President of Instruction gives the opening remarks to this program. However, Interim Vice President of Instruction Tim Cook is at a statewide meeting and was unable to attend today. Dr. Cook extends his congratulations and appreciation to Mike for sharing his expertise today. Mike Godson is the head of the Automotive Department at Clark College and has been a full-time faculty member since 1995. He is also a Toyota Technical Education Network, or T10 instructor. Mike is active in his profession. He's the chairman of the Toyota T10 National Advisory Committee, or Council, a National Automotive Technician Education Foundation, or NATEF, evaluation team leader, and the Washington Department of Ecology Authorized Emission Specialist. In addition, Professor Godson is Automotive Excellence, or ASE Master, and LI certified. Mike was named Educator of the Year during the 2009 North American Council of Automotive Teachers Conference, and that award is presented for excellence in automotive repair instruction. Before we begin the official program, I would like to thank the many people who made the Faculty Speaker Series possible. The Clark College faculty who so willingly share their expertise in research, the Clark College Foundation and community partners who provide the financial support for the series. I would also like to thank the Communications and Marketing Department who created and distributed the promotional materials for the event, the members of the Teaching and Learning Committee who contributed their time to review applications and select the faculty speakers. And I would also like to recognize Melissa Payne, the program coordinator for faculty development and outcomes assessment, for support and assistance in making the arrangements for today's event. At this time, I'd like to invite Randall Henderson, a student in the automotive program, to the podium to introduce Professor Godson.
My name is Randall Henderson. I'm a second-year automotive student at Clark College. When I came into the automotive program, I didn't know much about cars at all. And I'm checking out oil, everybody else. Didn't have a lot of confidence in having a career in automotive, and after being in this class for about 3 quarters now, 3 quarters, and 1 partial, I now have 3 ASE certification test pass, and I've learned a lot of valuable skills from Mr. Godson. Mr. Godson set a lot of goals for us, probably higher, exceeding most of the goals that we set for ourselves. And he doesn't just set them for us, he leads us to the goal. Instead of just setting goals, a lot of us just set them and don't have to really get there. With his support and guidance, I feel like I have the makings of being a good technician, and I think I will be one day. I think he's had an immeasurable impact on myself as well as most of his class, and that he's given most of us the tools, whether we use them correctly or not, it's up to us, but I think he's given most of us the tools to have a rewarding career. Mr. Godson.
Well, good afternoon, everybody. Thanks for coming out on this dark and dingy afternoon. I'm really excited about being here in the Faculty Speaker Series here at Clark. It's a great honor for me. I'll never forget the phone call Veronica Brock gave me saying, "Come on, you should do it, Mike." I don't know whether to blame her yet or thank her, so we'll see how that goes. At any rate, we're going to talk about some things about cars, automobiles of the 21st century, one technician's view. I'm going to come at a little more of a practical angle, really talk about technology that's out there today, not so much about what's in the future, and perhaps give you some information, or at least enlighten you on what to look for when you're trying to choose an automobile. So there are some core themes I want to talk about, and these core themes are going to thread through the entire presentation. The first one is people. When I first started in this business, all I wanted to focus on was the machinery. I've learned over time is that the people are what really make it happen, and the people are what really make it exciting. I tell students all the time, you know, I can teach anybody how to fix a car, but when you put a person next to that car or a customer attached to that car, that's when auto repair really gets interesting. Another theme is going to be safety. Safety is something that has really been advancing over the years. Ever since about the 1960s, we've taken some quantum leaps in terms of vehicle safety. And so you'll see a lot of that through here. And then I also want to touch on skilled labor and the importance of skilled labor today, particularly in our economy. I'm pleased that we have a large contingent in these departments here. Hopefully my comments will strike a chord with some folks. Okay, a little overview here. This is the stuff I'm going to talk about. A little bit of automotive history. I don't think we can talk about the future unless we know what the past has been. Advancements that have taken place over the years. Some safety efforts. Common current vehicle technology. Technicians and their jobs. And then there will be an opportunity for you to ask questions at the end. I'm hoping to keep it down to an hour, but Randall will probably tell you I can ramble on. So we'll see what we do. Automobiles really appeared around 1900 around the world, particularly in the U.S. Early vehicles and early cars were sort of all experimental, put together by crackpots and entrepreneurs. And as time went on, it wasn't until the early 1900s that a few individuals really took hold of the industry and started building vehicles in mass quantities. By 1950, cars had really defined many parts of American culture. And you notice the slide here of the driving. Without cars, we would not have a driving. Okay, and driving is part of everybody's lives today. In 1956, Eisenhower signed the Federal Highway Act and began construction on our interstate highway system. And since that time, America has been more mobile and connected than ever before. Another hallmark of the automobile really is freedom. Okay, automobiles represented freedom, and they still do in many cases. There are new markers of freedom out there, and I don't know if can anybody tell me one of the new markers of freedom at adolescence into adulthood is today? Well, young people all have to have that cell phone, right? Okay. We'll talk about that a little bit more when it comes to safety, but vehicle sales and a lot of manufacturers have been a little worried that cell phones are going to take over. They're not going to be able to sell many cars in the past. So let's look a little bit into the past here and explore what really took place around the turn of the century.
Hi, this is Kelly from Car Data Video. Today we're going to have a history lesson. Of all the automobiles that have ever been designed and built in the world, there's one that stands out as most significant above them all, and that's the Model T Ford. The Model T introduced mass production and single-handedly brought us from a horse and buggy level of technology to one where we had machines that were run by gasoline engines. Using a moving assembly line, Henry Ford was able to build these things at about 1/10 the time it took to build other vehicles by hand previous to the Model T. The Model Ts were simple, they were rugged, they were cheap, and as Henry Ford used to say, you can have any color you want as long as it's black. When they were first introduced in 1909, they sold for $950, which doesn't sound like much to us today. Back then, that was quite a lot of money. Henry Ford cleverly paid his employees $5 a day, which back then was a huge amount of money compared to other jobs that they could get. He also reduced their workday from 9 to 8 hours, but again, by doing that, he can have 3 production shifts working and hence build cars around the clock. All of this was going on at a time of economic difficulty and transition, and so the result of this is people would come from all over the country to get jobs working in Detroit at the auto factories, and of course their job of choice was with Ford. Production of the Model A's went for 19 years, from 1908 to 1928. And the last ones that were built that weren't very much different from the very first ones that he originally produced. They had wooden spoke wheels with metal rims pressed on them. You can see here what they're doing is hand filing the spokes to make them smooth so they can be painted. The engine was a ridiculously simple, by today's standard and light, 177 cubic inch, which is 2.9 liter, 4-cylinder engine, which produced 20 horsepower. The vehicle weighed about 1,200 pounds, depending on which body style you got, and would be good for about 40 to 45 mile an hour top speed. And it had 2 forward gears. The assembly line was split so that the frame and the wheels and tires and everything were assembled at one point, and then the bodies were assembled separately, and then at one point the body would be dropped onto the frame. Over the years, an enormous number of body styles were created. You had a touring car, a roadster pickup, a ton truck, a closed cab ton truck, a coupe, a 2-door, a 4-door, a Senador, a station wagon, and a convertible. Pretty versatile vehicle. Eventually the Model T was replaced by a Model A, which was a modernized, stylized version of a vehicle that looked quite the same. Highland Park was the first modern assembly plant. It's where the Model Ts were produced. And just like today, when they're done being assembled, they're driven off the assembly line. But look at these vehicles as they come out. Look at all the different body styles, many of which we read. And these are all just different versions of Model Ts. Finally, after 19 years of production, Henry Ford had actually built almost 15.5 million Model Ts. And they were by far the most popular and most plentiful vehicle on the road. And here you can see the assembly of the 15 millionth, which is a 4-door convertible model. And as you can see, they've added some paint colors other than just black. And that actually is Henry Ford there, driving off the assembly line and driving in that 15 millionth Model T Ford. This particular one hadn't gone through final assembly quality control. You can see how Henry had to give a little nudge there to get it shut properly. To start a Model T, you had to hand crank it, but because the engine wasn't very big and it was low compression, all it would take was about a half a turn and it would fire right up. Back then, riding in the car was an occasion. It was a big excursion. It was fun. Just the ride itself was quite entertaining. Keep in mind that going somewhere in a car was probably 10 times faster than going by horse or buggy, which is what they were accustomed to before. Back then, cities were just developing and most of the roads were terrible, especially the country roads. And so the Model T had to be built in such a way where it could handle anything, all the way from no road to city roads. And it actually did a very good job of that. Most of the country roads were mud roads or dirt roads, and in the city there were no snow plows. If it flooded, you had to ford it. And so you just had to deal with all this stuff. And the Model T was miraculous at being able to handle almost any road conditions you could imagine. So here you've got the original Ford Model T, the great-great-great-grandparent of most every car you see on the road today. This is Kelly from Car Data Video.
So that's just a little bit about where the automobile has come from. And really that was only 100 years ago. So the history of cars is not really that long, but we've come a great long way. Some technological advancements that have happened over the years. Vehicles were first powered by steam and mimicked railroad engines at the time. Cars like the Stanley Steamer had gasoline-fired boilers and an advantage over internal combustion because they did not require cranking like the old Model T. The advantage faded, however, when the electric starter was introduced. And they even had electric-powered cars in the early days as well, and they were generally marketed to women because they were easier to drive and take care of. But they were also very short-lived, giving way to the lighter and less expensive gasoline engine of the day. The first real giant step in auto technology was the assembly line, and you saw Henry Ford. That was his real contribution to modern automotive technology. Mass production is what drove the industry in the early years and continues to impact car companies today. In many ways, a car company's production system creates quality within a vehicle. So different car companies, say Toyota, their production system is what really makes their cars what they are. Government regulation has also had a significant impact on the cars of yesterday and today. Safety, air quality, and efficiency have all been moved forward by government regulation. The interesting thing for me is how many times the public views government regulation as an assault on personal freedom. Every time they try to make a change, everyone's screaming, well, what do you mean? I mean, what's going to happen if they really outlaw cell phone use because of distracted driving in the future? How many people are going to put those phones down and not use them in their cars? Computers have also moved auto technology ahead from many angles. Cars have multiple computers all networked together. These networks help eliminate vehicle wiring and can create customizable features accomplished through programming only. And flash programming is now becoming commonplace in the service stage of the repair process. Computers in design and production have changed the industry's core. Vehicle design and testing is largely computer modeled now, eliminating the need for large-scale prototyping, which was done in the early days. When I started in the business, it took about a minimum of 5 years for a manufacturer to bring the vehicle from drawing board to production model, and now the companies can do that in 6 months or maybe even less if they actually had to. So with that, let's look at a more modern automobile assembly plant. This is a BMW assembly plant. I think it's in Georgia. And this was put together by putting video cameras along the assembly line. And the main idea was they would sell a car to a customer, and that car could watch, or that customer could watch the car being built, their actual vehicle.
Congratulations on your all-new BMW X3. It was built in Spartanburg, South Carolina, at our newest assembly hall, which was created specifically for the X3. We even installed cameras along the assembly line so you could see your actual X3 being custom built. Every X3 begins its 2-day production journey in the body shop. Before it leaves, every inch is hand inspected from top to bottom. The paint shop is next, where a tracking system monitors every X3 as it moves through the corrosion protection, paint application, and finish processes. An environmentally friendly water-based paint is always used. From here, all X3s travel 1/3 of a mile through a tunnel to the assembly hall, where it all comes together. This is where the vehicle identification number is applied. At this point, the X3 officially becomes yours. The doors are removed from the vehicle and placed on a separate assembly line. This live camera captured your X3 as the panoramic moonroof was installed using state-of-the-art robot technology. Next, the wiring harness is routed through the cabin, trunk, and engine area. Here, your X3 was placed in a special conveyor that took it to the tilt area. The carrier allows associates to rotate your vehicle, giving them unobstructed access to the underbody. After tilt, your X3 returns to the skid conveyor, and the carpeting, headliner, and dashboard are installed. Next, it's time for the windshield and rear window. This was the actual windshield installation on your X3. The seats are installed next, and the doors are put back on the vehicle. The powertrain is assembled in a separate section of the hall, then moved to the marriage area. This is the moment when your X3 truly becomes an ultimate driving machine. Watch as the German-engineered powertrain was married to the painted body of your vehicle. This fully automated marriage line is the most innovative and modern in the BMW group. After the underbody and powertrain are aligned, robots tighten the bolts from the bottom. Then another set of robots aligned and fastened the front struts. Next, the X3's front end with a trademark kidney grille is attached. The wheels are mounted next. And here's your fully assembled X3, captured as it first touched the ground. The vehicle's fluids are added. The engine was started, and your X3 ran under its own power for the very first time. Next stop, your driveway. Enjoy your all-new BMW X3.
So a little bit different compare and contrast between the Model T line and the BMW line. There are some similarities though. You'll notice that the Model T line had their bodies assembled separately, and then the chassis and separately, and then they were brought together the same with BMW. The other thing is I've found over the years that I need to spend time with students on how cars are actually built. Most students have never seen a car being built in a factory, and they need that background to understand how to disassemble a car. Cars are not meant to be disassembled. That was never in the plan when they were built. So it takes some special processes and thinking in order to accomplish that effectively. Moving on here, safety efforts. The big push towards safer cars took place in the early 60s. Ralph Nader's book, Unsafe at Any Speed, presented a scathing look into the automobile industry. In '66, Nader testified before Congress, and in that same year, the National Highway Traffic Safety Act was passed. This created the National Highway Traffic Safety Administration we know today, commonly known as NHTSA. NHTSA's first director, Dr. William Haddon, recognized that standard public health methods and epidemiology could be applied to prevent automotive-related deaths and other injuries. He defined interaction between host, agent, and environment, human, motor vehicle, and highway, factors before and during and after crashes resulting in injuries. After proposing such an approach, NHTSA began requiring vehicle manufacturers to install safety equipment like seat belts, highways to be built with things like guardrails, and laws like prohibiting DUI and force. The result has been almost a continuous drop in injuries and fatality each year compared to the number of vehicles on the road. Thankfully, the improvement process continues today. The Clean Air Act is another piece of legislation that was a result of studies of air quality done in the LA Basin in the 50s. Hagen Schmidt was the researcher that actually did that initial research. And the studies identified motor vehicles as the primary source of air pollutants in that area. Everybody thought it was point sources, all the refineries and the factories, but no, it was in fact the cars. This moved California to form their own Air Resources Board. The board required vehicle manufacturers to meet certain emission standards beginning in 1968 and further led U.S. legislation to amend the Clean Air Act in 1970. This landmark law continues to improve our lives and touches us every time we have our car run through the emission station to get the license every couple of years. The last effort here is an independent effort. The Insurance Institute for Highway Safety, or IIHS, is a research and advisory body that focuses on vehicle safety. You probably know them through their crash test ratings and research. They actually have a pretty nice website if you're looking into the safety of a particular car. So one thing I hear from a lot of people is they continue to say, oh, those old cars, they were bigger, heavier, they're way safer than cars of today. So to celebrate their 50th year, the Insurance Institute for Highway Safety did a crash test. This is an offset frontal crash test about 40 miles an hour with a 1959 Chevrolet and a 2009 Chevrolet. It's buffering in. I was worried about this. There it goes.
That's the Insurance Institute for Highway Safety's front crash of a 2009 Chevrolet Malibu and 1959 Chevrolet Bel Air. In slow motion, you can see the differences in how the new and classic cars perform in this version of the traditional frontal offset test. The Institute conducted this test to commemorate its 50th anniversary. It dramatically shows how much improvement has been made in passenger protection since the non-profit organization opened its doors. The two cars collide in an explosion of metal, glass, and plastics. Where the Malibu crumple zone absorbs much of the crash forces ahead of the windshield, the Bel Air structure allows the blinder car to compress the passenger compartment. The impact is made worse for the Bel Air driver by the lack of airbags, head restraint, and even a seatbelt. As a result, injuries to the neck, chest, and both legs would be likely. Consequently, the Bel Air receives a poor rating across the board. On the other hand, the modern Malibu provides good protection, with the dummy movement being well controlled. Measures indicate a low risk to most body regions, though a foot injury would be possible. Beyond the safety gear, advancements in vehicle engineering give the Malibu a clear advantage in this matchup. While classic cars are often considered to be rock solid, this 59 demonstrates how much better today's cars are. And the IHS has played a key role in driving these advancements. In the past 50 years, the Institute has made a real impact. The roads today are safer for it.
For complete safety information, subscribe to consumerreports.org.
Okay, so it's a little surprising there, and I think a little bit of a shock factor with that. But I really think it does demonstrate how much safer newer cars are than cars of the past. So let's talk about another safety device that's on all cars, and I consider a safety device is tires. Tires have evolved from solid rubber in the early 1900s to advanced air-filled constructions of today. I've talked to people about tires before World War II, and flats were commonplace. Local people that would take a trip to the beach, say 1930, 1940, having one flat during that trip was a good trip. Okay? You might have more than one. Today, tires can run 50,000 miles or more without any service required other than inspecting and maintaining their air pressure. Constructed of rubber collected from trees, synthetic compounds, and steel, tires provide the connection between the vehicle and the road surface. In my mind, there's no more important safety device. You may be surprised at the number of components that are inside these round black donuts, and that your life depends on those every time you get on the road. One new advancement is run flat tires. You might have heard of run flat tires. Run flat tires are designed with a stiffening insert in the sidewall, so if all the air runs out, you can drive the tire for maybe 50 miles at 50 miles an hour, so you can get off the highway and not have to change it. Lastly, I'll talk about some TPMS. TPMS stands for Tire Pressure Monitoring Systems. And this was another result of another piece of legislation that came through NHTSA. And all cars built after 2008 have this particular system. So this is a cross-section of a basic tire today. You can see it has an inner liner, which is a special type of rubber. It has the bead wires. Those are steel cables that run around the inside of the tire. It has the actual carcass, or the plies as they're called. It's rubber and usually polyester 40. The sidewall and the tread are also two different types of rubber. And then we have the belting. The belting is what keeps things from puncturing through the tire and gives it ultimately its strength. Another basic thing about tires, and this is actually fairly old now, they used to have bias ply tires in the early days, and bias ply tires had the cording or the carcass ran at 45 degrees to each other. It created strength, but it also created rolling resistance and also distorted the tire contact patch. Radial tires came along in the late 70s and sort of took over for bias ply tires because they lasted longer, they created less heat while they were rolling because they didn't flex as much, less rolling resistance, better mileage. And today, pretty much everything has a radial tire on it. So you might find bias ply tires on maybe a trailer or a piece of industrial equipment. That's about it. So you ever wonder how a tire is built? Let's see how a tire is built.
A tire is round and is like. However, you examined all the manufacturing stages, you would realize what a complex product like beneath this plain exterior. In actual fact, leaving the natural and synthetic rubbers aside, more than 200 different materials are combined to manufacture the tire that we know so well. There is carbon black, silicone, and sulfur, plasticizers, vulcanizing agents. But there are also pores, a lot of pores, which in fact can be either steel or fabric such as polyester and Kevlar. These different raw materials are used to produce a wide variety of components. Flat or profile products, steel cord or fabric plies, and also bead wire. These components give the tire its elastic properties, ensure its resistance to wear, provide adhesion, and determine its service life. It all begins in the tire building drum, which is a rotating cylinder with a flexible center so that its edges can be brought closer to each other. You'll see why in a minute. A thin, perfectly airtight sheet of synthetic rubber must first be laid down on the drum. This will act as an inner tube inside the finished tire. The second layer is called the casing ply. Why? Because it contains the framework of parallel fabric cord, which we call the casing. This assembly is the vital substructure and consequently a key component in the radial tire. Set tightly against strips of profiled rubber are two high-resistance steel wire hoops, which are known as the bead wires. They hold the tire firmly on its rim. The casing ply is then folded up over the bead wires to hold them securely in place. Other components are added with the same degree of accuracy. Some tires have dozens of them. But don't worry, we will not describe them all in detail. However, take a look at the sidewalls. They are made of rubber, both flexible and tough, to protect the tire from side impact. Then, by inflating the central part of the drum, its edges are brought closer to each other. The tire is shaped. The reinforcing tread plies providing directional stability and mechanical resistance have yet to be added. Fine but highly resistant steel core strengthens these plies. Being laid crosswise to the casing block, it forms shape-retaining triangles. Now it's time to lay down the tread rubber. It is this part of the tire which will have a tread pattern and will be in contact with the road surface. The unfinished tire is then put into the curing mold, which has all the tire markings and the tread pattern. A curing bladder filled with hot pressurized water forces the rubber back into the mold cavities. The hot water and steam around the mold start the curing process. This curing, or vulcanization, chemically bonds the rubber compounds to the steel and fabric cord reinforcement components. During this chemical reaction, the tire goes from a plastic to an elastic state. Sometime later, the transformation is complete and the tire emerges from its metal shell. The tire has been given its final features and finished shape.
Michelin, a better way forward.
Okay, so probably more than you ever really wanted to know about tires, but I really want to make a point that they're a complicated construction. And again, your car depends on those tires to maintain contact with the road. Tread contact patch might be this big, maybe even a little bit smaller than this. Okay? You only have 4 of these. You've got 2,000 pounds of steel and plastic and rubber careening down the highway. You better make sure that this part is working. Run flat tires, they're the same as a standard tire, other than they have these sidewall reinforcing inserts. So if the air runs out of the tire, then you can continue to run the tire. These particular cars will all have tire pressure monitoring systems because they need to notify the driver when the tire is out of air. You can't continue to drive a tire with no air in it forever. But also, generally these cars don't have spare tires because they don't need them. They can just drive off the highway and get their tire repaired. Heat is also a real enemy of the tire. You notice how they vulcanize the tire together with heat. If you continue to heat the tire, it's going to break down. And as the tire flexes, it heats itself up, and the heat is what really destroys the tire. So keeping good air pressure in the tire is very, very important. So tire pressure monitoring systems. These have been put on all cars since 2008. And they were really developed in the racing community. Racing sanctioning bodies like Formula One have been using these for years. They actually have a pressure and temperature transponder in each tire, and then that transmits information to a receiver and then to a computer. And that computer's programmed to watch each one of these transponders and then notify the driver by turning a light on if the tire pressure goes low. And I've got another little video clip here about this. And this will also explain what the Tread Act is and where it came from. Some of you might have heard of Ford Explorers and Firestone tires. A few years ago, this is really what the result of that was.
I was at NHTSA from 2002 to 2006. My role at NHTSA was to be the chief counsel of the agency for about 3 years, and subsequently I became the acting administrator of the agency. I was chief counsel during the time that NHTSA was responsible for implementing all of the regulations and rules and procedures that were required by the Tread Act. The Tread Act was enacted by Congress in response to the Ford Firestone situation, and it included a large number of new regulations that NHTSA was directed to implement. One of them had to do with tire pressure warnings. And one of the things that was found during this time is that consumers do not keep their tires properly inflated. And keeping tires properly inflated is very necessary for both safety, and it actually also helps to promote fuel economy. And so NHTSA came about to develop a regulation that would provide people with a warning to say, one of your tires is becoming significantly underinflated and needs to be serviced. And this warning operates independently of any activity from the consumer, so that consumers are always told one of your tires has a slow leak that needs to be addressed. I believe that NHTSA would still want consumers to know how important it is to maintain your vehicles and to keep your tires properly inflated. It's absolutely essential to keep your family safe on the road. It's absolutely essential to obtain from your vehicles the best fuel economy you can possibly get. And it's absolutely essential that consumers understand what the signal is and what the warning is that tells you one of your tires is low, and that you respond to that warning and go to your dealership or your service facility as soon as that comes on. And when NHTSA makes rules for cars, NHTSA does not mandate a design or a technology. NHTSA sets a performance requirement that every vehicle has to meet when it's tested in accordance with a certain way. And so when NHTSA made the tire pressure warning regulation, as it does with all regulations, NHTSA established a performance requirement that can be met through varying kinds of technologies. At the time that the Tread Act was enacted, at the time when NHTSA was developing its regulation, there were essentially two types of systems, an indirect system and a direct system. NHTSA did not mandate either one, but it set the guidelines and will allow technology to develop as long as technology meets the performance requirements that NHTSA has set, which are all designed around the way people will use the cars and consumers will actually respond to warnings and signals, then NHTSA will allow that technology. But every technology that's used has to be able to meet all of the very specific and very rigorous requirements that NHTSA set up to protect consumers. The TREAD Act was a response to a particular situation. NHTSA is an organization which has existed since the 1960s. It is all about keeping people safe. I had the great benefit and opportunity to be part of the organization for a few years, to work with the dedicated staff at NHTSA to enhance and ensure safety on our roads. This involved not only developing significant regulations to make sure new safety features are put into motor vehicles like TPMS systems, but also to help educate people on all of the things that you can do to keep yourself safe. And that involves not only keeping your tires properly inflated, but also always wearing your safety belts and never drinking and driving. All vehicles that are sold today have TPMS systems embedded inside them. I have a new vehicle during the winter time recently. The light went on. I took it to the dealership. They inflated my tires, made sure I was safe, and away I went.
Okay, so has anybody ever seen that light? The side of the tire with the little exclamation mark. It's amber in color. One thing I always tell my students about lights is there's three basic colors of lights. There's red, yellow, and green. What does that remind you of? Right? So when they're red, what do? Okay. When they're yellow, it's caution. Okay. Green means go. You can go. So these lights are amber, and my experience has been with them. If your light does come on, and in cold weather, it's very common for that to happen because your tire pressure sort of the tires contract and the pressure goes down. Usually you just have to air your tires up, check the pressure in all of them, make sure they're to the manufacturer's specification on the car, not on the tire. Drive your car for a few miles and the light goes out. No big deal. Ultimately, technicians are the ones that are responsible for these systems to make sure they continue to work. You should probably think about that. Also, it's against the law to disable any of these systems. So technicians cannot go in and turn your light out because part of the system doesn't work, like the little transponders. They have to put new ones in. Because they're not only trying to keep you safe, they're trying to keep everybody else safe. Okay, this is something that I'm really excited about. The new computer-controlled chassis technology that's out there is awesome. Cars handle today like never before. And most of the drivers don't even understand what's on the car or that the car is actually helping you drive it. It's actually assisting you as you go through limited track conditions. There's been sort of an evolution of the system. Electronic stability control, you may have heard, is really the system that is doing most of the really good stuff now. But you had to have ABS and traction control on the cars first. All vehicles built 2012 on are required to have electronic stability control. And really that was a result, again, of NHTSA legislation and then the government, federal government, realizing what an advancement this was. So let's talk a little bit about these systems. So basic ABS. Basic ABS is a system that controls braking on each wheel. So you have your hydraulic brakes here that are connected to a hydraulic brake actuator through the master cylinder. And then you have wheel speed sensors. And the wheel speed sensors are electric and they feed data up to your skid control or ABS computer. The way the system works is if the vehicle's in a braking situation and the skid control ECU judges a tire slowing down too quickly, basically skidding, it'll engage the ABS and start controlling the wheel itself, the wheel that's actually slipping, so the vehicle can brake in a straight line, and you can also turn the vehicle while you're braking. If you were to skid and try to turn your car, you're going to keep going straight ahead. ABS will keep you from doing that. So here's a little, this is a little Toyota clip here. Are you kidding me? Well, I'm just going to have to move on. The link must be broken. That's okay. We'll continue to go on here. Tire traction is what ABS is all about. And keeping the tire slip ratio between 10 and 30% is the primary area where you're going to get the most stopping force out of your tire. So 100% is going to be locked up, 0% is going to be a free wheel. So what's going to happen is the ABS system is going to try to adjust that slip ratio by controlling hydraulic pressure in each individual wheel to keep it in that range. You can also see on this diagram here that traction on dry concrete is way more than it is on ice. And these systems will actually work quite well in slippery conditions and allow you to control your car when in other cases without it, you wouldn't be able to. The wheel speed sensors, this is a passive style sensor. They've made advancements since this, but this is the simplest style. It's really just a coil of wire with an iron core and a magnet. And that magnet creates a magnetic field around that coil. And then you have a steel rotor or a sensor rotor there on the diagram. As that sensor rotor rotates connected to the wheel, the little teeth align with the core of the sensor, and it makes the magnetic field fluctuate. As it fluctuates, it creates a small electric current in that winding, resulting in an AC waveform that you can see on the right-hand side. The computer can count the frequency and then calculate speed based on that. The hydraulic actuator itself, I mean, this is a little complicated looking, but this is really what's inside one. You have each of your brakes here, and then each brake is connected to a pair of solenoids. And those solenoids have a little valve inside. You have the pressure holding valve, which is this one, and the pressure reduction valve. When you flow current through the winding that's around these, it makes those little pintles move, either opening or closing the valve. Perfect for a computer, right? It's either on or off, 1 or 0. And then we have each one of these circuits for each hydraulic circuit. We also have pumps, okay? And we have a hydraulic pump that will use hydraulic brake fluid and pump it. In this case, all it's going to be there for is to recirculate the fluid. The driver creates all the pressure in this system. During normal braking, the system's turned off. You don't need it. So the pressure holding and pressure reduction valve are just left in their resting positions. You get hydraulic pressure from the master cylinder directly through to your brake. No problem. If for some reason the hydraulic actuator becomes electrically disconnected, you're still going to have your normal brakes. When the vehicle senses ABS braking situation, what's going to happen is the first thing it's going to do is go into what's called pressure holding mode. And it's going to energize the pressure holding valve so that the pressure in the brake line here is going to be maintained statically, no matter how much additional pressure is put on the brake pedal itself by the driver. And what it's going to do, what it's doing here is the wheel's slowing down too quickly, so it's stopping the hydraulic pressure and then it's watching the wheel speed. If the wheel continues to slow down too quickly, then it goes into reduction mode. And reduction mode has both solenoids turned on, and this reduction valve here allows brake fluid to go back up through the pump and the reservoir. And so now the hydraulic pressure in the wheel is getting reduced. And what's going to happen is the wheel's going to begin to speed up. As the wheel speeds up, then it's going to go into pressure increase mode. And pressure increase mode is again going to turn off both solenoids and allow pressure from the master cylinder into the brake. Really what this is just a very rapid pulsing or pumping of the individual brake. Much faster than a driver can do it. 15 times a second is probably even maybe a low estimate. It might go faster than that. If you've ever been in an ABS braking situation, you can feel feedback or almost a vibration from the pedal, kind of a growling almost. This is a diagram of what happens to wheel speed here in an ABS braking situation. So here the wheel speed is beginning to slow down too quickly. And you see, first thing we go into holding mode, then reduction mode, holding mode. and then we go increase holding as the wheel begins to speed up again. If it speeds up again to regular vehicle speed, it's trying to keep it in that slip ratio range. Then it begins to slow down too quickly. Again, reduction mode, and then continues to pulse. On the bottom here, you can see a depiction of the brake cylinder hydraulic pressure itself. ABS, before I go into traction control, ABS braking, I mean, a lot of you might have learned, or maybe your dad or your uncle, when you're braking, you should try to pump the brake, right? To make sure that you can slow down effectively. With ABS brakes, you don't do that. You push the brake down and hold it and let the vehicle do the work for you. So, apply the brake and steer. That's ABS, right? That's all you need to do. Don't pump the brake. If you let off on the brake, the ABS system's going to quit and you're going to disable that advantage that you have. Traction control was the next addition to this system. And what it did is, while you're accelerating, and one wheel starts spinning, because there's a differential in the axle, it'll apply the brake to that spinning wheel, so the wheel that has traction can grab. What that's going to do is allow your vehicle to accelerate in a straight line, rather than try to turn to one side or the other. The other things it would do is send a signal to the engine control computer to start limiting engine torque in various ways, either by disabling injectors or backing off the ignition timing. But again, this came from racing. You can accelerate much faster with traction control than without it. Now, a lot of my students, they say, oh, that traction control, I can't burn rubber anymore. Many of these systems, if you really need to disable it, you just push the track button and you hold it for more than 3 seconds, and generally speaking, it'll disable it, and then until the next key cycle happens. What they did with traction control is they just added in another pair of solenoids to the ABS system. They put in larger pumps that could pump more pressure, and now the computer can actually create hydraulic pressure in the brake system without the driver pressing on the pedal. Great stuff. Then with that, now what we can do is we can add vehicle stability control, or as it's commonly referred to in the trade, electronic stability control. Electronic stability control will help your vehicle when you're driving and steering or turning to keep it from understeering, which is called plowing out, where you try to turn but the vehicle keeps going in a straight line, or oversteering, where you're actually turning, and then what happens is the back of the vehicle breaks loose, and then you loop out, so to speak. In an understeer condition, what the ECU does is reduce engine power and then apply brake pressure to the front wheels and the inside rear wheel, and that helps turn the car. In an oversteer condition, again, it reduces engine power output, but applies the brake to the outside front and sometimes the outside rear, right, to keep the vehicle going in a straight line. In order to make this system work, they needed a couple of additional sensors. One is the yaw rate and deceleration sensor. This is a sensor that's bolted in the middle of the car, and it electronically transmits acceleration, deceleration, and yaw rate information to the skid control ECU. So you can see all the directions that it can actually tell the vehicle is moving. It's very similar to a Wii game console, that you bowl on, right? Or you play baseball or you golf. It has one of these sensors built into hand control, and so it can tell the direction that you're moving. The other device that you need is the steering angle sensor. So the system has to know how much steering input that the driver is giving the vehicle. So it knows how much steering input the driver is giving the vehicle. It knows the direction that the vehicle is traveling, and then it can engage the stability control to help control the car. Again, great stuff. These cars today, snow and ice, you can step on the throttle, it'll go in a straight line, you can brake and go around a corner, no problem. They're so seamless you can barely even tell that you're having a problem. The last iteration here is vehicle dynamic integrated control, or vehicle dynamics integration management. This is where you sort of blend all the systems together. And the reason they can do this now is they can it's all programming. They have all the pieces of equipment on the car. Let me see if this is going to plug here.
Keeping the vehicle within the realm of stabilized performance can be compared to controlling the ball on a smooth round surface. This indicates that once the realm of stabilized performance is exceeded, it is quite difficult to regain stability. The first thing developed to help rectify this situation was ABS. This prevents wheel lock and makes steering operation possible when the brakes are suddenly applied, helping the driver's ability to avoid danger on slippery road surfaces. This is similar to building a safety barrier around the flat round board to prevent the ball from flying off the surface when braking. Next came the traction control system. By adding the ability to drive efficiently on the road, it helps avoid unnecessary wheel spinning and stabilize vehicle behavior on slippery road surfaces. What has been drawing attention in recent years is VSC, a vehicle stability control system employed when the vehicle begins skidding. In this way, a safety margin was constructed in all directions. An assistant to assist the driver in unforeseen circumstances was made possible. Because all these controls were implemented once a limit had been crossed, the sections where the various areas connected were not smooth when each of the individual controls was combined. And because braking control is not linear, a certain jaggedness remained in some areas. But with the newly developed VDIM, these are controlled jointly, and the areas connected are smooth and seamless. Furthermore, coordination with the driver's intentions and intervention are made before the safety limit is reached, making safe driving feel more natural. An easy way to understand this is to compare it with a squarish ball transforming into a completely round ball. As you can see, vehicles equipped with VDIM have smooth and simple handling.
So I think you can see that the surfaces they were on were very slippery, and the cars with the vehicle dynamics integration management could control just seamlessly through those cones when a normal vehicle would just be hauled over the road. And drivers today don't even really realize that that stuff's happening because it's so smooth in the way it's implemented. This clip is really meant to heighten awareness about computer technology in cars. And it's a semiconductor manufacturer's sort of depiction of one of their systems called partial networking, where it can bring a network of computers up and then put some of them in partial networking mode. But it's a pretty good illustration of what actually happens today when you walk up to your car. So here, this is pretty short, but just watch this. How to deal with today. That's the way cars are built, and it's not going to change. So with that, let me talk a little bit about technicians here. As technology advances, the need for skilled workers won't go away. I would contend our lives depend on these individuals more every day. Mechanical skills of the past remain needed, but new high-tech abilities are already part of an auto technician's job description. I've been involved in this evolution and even resemble the picture of James shown above here. I look at him and I wonder what he's thinking about. In my experience, most automotive technicians are extremely intelligent individuals with outspoken opinions. Independence also defines the breed, reinforced by self-agency and control over complicated machinery that other lives are dependent on. But dirty hands continue to stain our reputation, like tattoos resulting from a drunken night on shore leave. Public perception surrounding what technicians do seems steeped in folklore, or fear of being ripped off. These truths continue to impact the lives of me and my students, sometimes on a daily basis. Matthew Crawford studied physics at the University of California, Santa Barbara, and then turned to political philosophy, earning a PhD from the University of Chicago. He has published articles on ancient Greek philosophy, neuroscience, and a book entitled Shop Class's Soulcraft, an inquiry into the value of work. Crawford is currently a research fellow at the Institute for Advanced Studies in Culture at the University of Virginia, and has this to say regarding skilled trades. A gifted young person who chooses to become a mechanic rather than to accumulate academic credentials is viewed as eccentric, if not self-destructive. There is a pervasive anxiety among parents that there is only one track to success for their children. It runs through a series of gates controlled by prestigious institutions. Further, there is a wide use of drugs to medicate boys, especially against their natural tendency towards action. The better